One of the major disadvantages of the Friedel Crafts alkylation reaction is that it doesn't work with all primary alkyl halides. So, for example, the one that we have up here is a primary alkyl halide because the carbon that's attached to the chlorine, the one that's we're highlighting right now, this carbon is only attached to one other carbon, and so we would say, well, that's a primary, but this one carbon that it's attached to is also attached to other carbons as well. And so this is a primary alkyl halide, but since it's a little bit longer than some of the other ones we've seen, we're going to actually have a different product for the major product. And we're going to go through the mechanism to see how come this product is actually the major one instead of just replacing that H with this alkyl group like we did for the minor product. So we could still get some minor, but a lot of it is going to be this other product that looks a little bit different in the structure. So for the mechanism, we're going to go through it stepwise like we would. So we have that first step is going to still be the same. The chlorine is going to complex to the AlCl3. But at this step, it's going to sort of combine what we saw in the previous two videos in terms of we're going to end up kicking that great leaving group out. So remember, this was our great leaving group. We saw in methyl, we had the benzene come in and kick that out, and that's what would happen to get that minor product. At this point, the benzene could attack that super electrophile, make that leaving group leave. What can happen instead, though, and let's maybe number our carbons, what can happen instead, before the benzene can even get a chance to attack this, because carbon 1 has such a large delta plus, so we have a large delta plus on carbon 1. It's almost as if carbon 1 is a carbocation. And we saw that primary carbocations are really not stable. And so it's almost like in this molecule, because that carbon 1 is so electron deficient, it's almost like it's a full out positively charged carbon, which is not very stable. So what's going to happen instead is we actually have these two H's sticking off of carbon 2. One of those H's is going to do a hydride shift and actually make a full out carbocation, but just on a more substituted carbon. And so that's kind of that driving force behind this reaction. So to show that hydride shift, we're going to start in the middle of the bond. We're going to point directly at carbon 1. And because that hydrogen is basically taking its electrons and attacking carbon 1, we're going to make the leaving group leave off of it at the same time, or else carbon 1 would be overloaded. And so this is our hydride shift. And this, because it's happening in the same molecule, happens a lot faster than waiting for the benzene to come and attack. So now we're going to have still one H attached to carbon 2. That's going to be a full out positive charge. Our other H is attached to the end, so carbon 1. That's the H that moved. So we basically took the electron density from that H and made it into a bond there. That kicked off the leaving group at the same time, so we can draw that leaving group. Because it's now gone, and we have a different looking carbocation at this point. So that is actually our superelectrophile, just like we saw with the secondary and tertiary. Carbocations can also be superelectrophiles. And this one got generated a little bit differently. It's kind of like a hybrid, I would say, between the two mechanisms we've seen so far, because we can't just have the leaving group leave because we couldn't make a primary carbocation, but we still go through a carbocation because we have this hydride shift due to carbon 1 just being very, very electron poor. And so we do get that super electrophile. That means when the benzene goes to attack, we're going to be connected a little bit differently. So we're going to have on carbon 2, we'll leave off that hydrogen that we were showing. So carbon 2 is going to have that positive, so when the benzene comes to attack, it's going to attack carbon 2. That's going to give us this structure where now the attachment point is on carbon 2. Carbon 2 has still its one bond to carbon 1. So let's draw that one out. I just decided to make it go up. Then carbon 2 is also still attached to 3. And then carbon 3 is still attached to 4. And so that's where that kind of branch structure is coming from in our major product. We're actually attacking at carbon 2, and that's where the point of attachment is to the ring, and so that's why it's branched. If we were making the minor product, we would just attack carbon 1, and then we would just have the line like that, just kind of in our normal mechanism like we did with methyl and our ethyl halides. But as soon as you start to have a carbon beside that can actually make a secondary carbocation, that's when you have this hydride shift happen. And so we get that product, and then we just have to regenerate our aromaticity same way that we always do. So we're going to take the H. The Cl minus can do this. To get our final product, and this is our major product because we were able to make that secondary carbocation. So this will happen with primary alkyl halides. That are 3 carbons or longer. So if you see a propyl halide, so if you have just 3 carbons, this one had 4. If you had only 3 carbons, you could still do this because you could still make that middle carbon into that positive charge, and it will happen that way, and you're still going to get that type of major product. And so methyl is only 1 carbon, ethyl is 2 for the primary alkyl halide, so they're fine because you can't make a substituted enough carbocation. With ethyl, we would have a primary carbocation if we did the same hydride shift, and so you don't have that happening because there's no driving force to make a really unstable carbocation. But as soon as you get 3 carbons or longer, you're able to make the secondary carbocation from the carbon beside the one that's attached to the good leaving group, and so that's when the hydride shift starts to happen, and that's where the problems start to come in. So what we're going to see in the next video is a different type of reaction that can kind of help take care of this problem and another one that we haven't mentioned yet, and we can end up still being able to make molecules like this. We just would have to do it in more than one step, basically.